Good morning, students. Today we are going to discuss about the second part in the PN Junction diodes. In the previous class, we discussed about the different types of material, the classification of material, conductors, insulators, semiconductors, and also discussed about the electrical characteristics of the conductor, insulator, and semiconductor. And also we discussed in the class about the energy band diagram, atomic structure and energy band diagram of inductor, semiconductor, insulator, and also discussed about the intrinsic semiconductor, extrinsic semiconductor. In the extrinsic semiconductor also discussed about the n-type material, n-type material energy band diagram, p-type material energy band diagram we discussed. In this class we try to discuss about importance of hole, generation of a hole, movement of a hole. So in this, after completion of this period, you would be able to understand the importance of the hole and generation of the hole and movement of the hole. Let us see in detail. Absence of an electron in a covalent bond is called as a hole. Hole is a positively charged particle. Coming to our electronics, in the electronics, mainly current transfer is because of the free electrons. The free electrons are moving from plus to minus, or we can say that the electrons are attracted by the positive positions, that is wherever there is no electrical charge is there, that position is called as a hole. The absence of an electron absence of an electron in a covalent bond is called as a hole. Hole is a positively charged particle. Hole can be generated by thermal energy, and second one is the doping. How we can generate the holes? Hole is nothing but a absence of the electron in the covalent bond is called as a hole. So that is the equal amount of attraction is there, equal amount of properties are there for the hole, but this is the opposite to the electron, that is the absence of the electron. Generally in the electron, this is also treated as a one of quantity like the electron. Hole also having the same importance as the electron. Hole can be generated in two ways: thermal energy and doping. Thermal energy means we need to apply the thermal energy to the material so that the covalent bonds may be broken. So from the broken covalent bonds, holes and electrons are generated. The next one is the doping. Doping is nothing but adding the impurities to the pure form of the material is called as the doping. If you add the impurities, so less number of holes may generated, or more number of electrons may generated, or more number of holes may generated. Like this, holes and electrons are generated. The first one is an application of an external energy. An application of an external energy equal to 1 electron volt, a covalent bond breaks. If we apply the 1 electron volt, the covalent bond will be broken. When the covalent bond breaks, an electron crosses the gap and enters the conduction band. leaving a hole in the valency band. That is, whenever we apply the 1 electron volt energy to the covalent bond, what happens means an electron crosses the gap and enters the conduction band. When it is moving to the conduction band, the hole will be generated in the valency band. Hole will be generated in the valency band. Free electrons are available in the conduction band. Holes are available only in valency band. Holes are available only in valency band because electrons are moving from valency band to the conduction band. So the absence of the electron is called as a hole. Now you can see the silicon, that is a semiconductor material. You can see silicon atom is covalent bonded with other atoms. Silicon having the four outer orbital electrons are there. These four are outer orbital electrons bonded with the other four silicon atoms. So this bonding is in the form of the covalent bond. Whenever we apply 1 electron volts to this atom, so what happens means the covalent band is broken. After broken the covalent bond, the free electron moves from the covalent bond to the conduction band. So that absence of the electron is called as a hole. You can see in the diagram. When the free electron is generated, the hole will be created in the covalent bond. The next one is the hole generation due to the doping. Doping is a process of adding impurities to a pure semiconductor. Doping is a process of adding impurities to a pure semiconductor by adding trivalent atoms to pure form hole is created. If you add the trivalent atoms means 3 outer electrons atom to pure form of semiconductor, then hole is created. For example, gallium atoms are added to a pure semiconductor to create a hole. I already mentioned doping. Doping is a process of adding impurities to a pure semiconductor. By adding trivalent atoms to pure form, hole is created. For example, gallium atoms are added to a pure semiconductor to create a hole. So in this way we can generate the holes. That is, you can see, so in the atomic structure we having the silicon and we are added the gallium, or we also say that doped with the gallium atom. Gallium atom having the 3 valency electrons are there. The silicon atom having the 4 valency electron. By using the 3 silicon atoms, it will forms the covalent bonds. For one covalent bond, 1 electron is more required. Thus necessity of the electron is called as the hole. The absence of the hole is called as a electron is called as a hole. Like this, if n number of gallium atoms are added, n number of holes are generated. Like this, we will generate the holes in the atoms by applying the external thermal energy or by adding the impurities to the pure form of the semiconductor. Like this, we will generate the holes. So now once again we try to discuss what we discussed. The absence of an electron in covalent bond is a hole. We define that absence of an electron in covalent bond is a hole. A hole is created due to doping and thermal energy. The hole is created by using the doping and thermal energy. Holes are moves only in the valency band. Holes are moves only in the valency band. So we having in the valency band. The next we try to discuss about on completion of this you would be able to understand what is doping, what is a hole, and we also discuss about the extrinsic semiconductor and formation of P-type and N-type semiconductor. So on completion of this period we would be able to understand the what is doping, what is a hole, extrinsic semiconductor, N-type semiconductor. Doping. What is the doping? Doping is the process of adding impurities to the pure semiconductor is known as a doping. So generally adding the impurities. What is the meaning of impurity? Means pure form of the semiconductor having the less number of free electrons. In order to get the more number of free electrons or more number of free holes, we try to add the some other external material, external atoms. So generally the semiconductor material having the valency electrons having the 4 electrons are there. So in order to get the more free electrons we need to add the atoms such that the valency electrons may be 3 or the valency electrons may be 5. If we add the 3 valence electron, that is called as a trivalent electrons. If you add the trivalent atom to the pure form of semiconductor we will get the holes. If you add the pentavalent atoms to the semiconductor, pure semiconductor, then we will get the more number of free electrons. So this process is called as the doping. Doping is the process of adding impurities to the pure semiconductor. Doped semiconductors are called as extrinsic semiconductor. Doped semiconductors are called as extrinsic semiconductors. Impurities are either pentavalent atoms or trivalent atoms. We may having the two types of atoms, pentavalent and the trivalent. I already mentioned the need of the trivalent and pentavalent. Why? Because if you having the 4 electrons in the semiconductor material to form the covalent bonds it need the 4 electrons, but if you provide the 3 electrons what happens, it requires extra electrons. That extra electron is called as a hole. If you add the pentavalents 4 electrons and this 5 electrons, 4 may form the bond and 1 electron is the extra electron, so that is act as the free electron. The meaning is if you add the pentavalent it will generate the more number of free electrons. Extrinsic semiconductor. If we add an impurities to pure semiconductor to increase charge carriers, this form is called as extrinsic semiconductor. Adding the impurities to the pure semiconductor is known as the extrinsic semiconductor. Pure form of the semiconductor is called as intrinsic semiconductor. In extrinsic semiconductor, charge carriers increases without breaking the covalent band. So in order to increase the charge carriers we need to apply the external energy, and that external energy breaks the covalent bond. But in the doping phenomena, we need not to break any covalent bond. If you add the impurities, the free electrons and holes are generated without breaking the covalent bonds. That is the advantage of the doping. Pentavalent atoms have 5 valency electrons. These impurities donate electrons to conduction band of semiconductor atoms. As I already mentioned, these will donate the free electron to the conductions. That way, pentavalents are called as a donor atoms. Examples are the phosphorus, arsenic, antimony. Phosphorus, arsenic, antimony. So these pentavalent valency electrons are called as a donor atoms. Atomic number of phosphorus is 15. Therefore, number of electrons in the phosphorus is 15. The outermost orbital it having the electrons of 5 electrons. It have outer orbital having the 5 electrons. That way it is called as a pentavalent. Next one is the trivalent. Trivalent having the 3 valency electrons. So when the 3 valency electrons are there, for the forming the full covalent bond, they accept the 1 extra electron. These atoms accept the electron from semiconductors. That's why these trivalent valency electron or trivalent atoms are called as the acceptor atoms. Trivalent atoms are called as the acceptor atoms. Example is the aluminium, boron, gallium, indium. So these are the trivalent atoms. We may dope the pure semiconductor by using the pentavalent, that is the donor atoms, trivalent, that is the acceptor atom. We can use any of the donor atoms will donate the free electrons, acceptor atoms will accept the free electrons. The boron atomic number of aluminium is 13. So it having the 13 electrons. So 13 means in the outer orbital it having the 3 electrons. To form the covalent bonds, 3 electrons are needed. But in the semiconductor we may having the 4 electrons. So another 1 electron is empty. So that empty electron always accept the electron from the free electrons. That's why it is called as a free electron. So now we try to discuss about the hole. What is the hole? Absence of an electron in covalent bond is called as a hole. You know already. Absence of an electron in covalent bond. A positively charged particle is called as a hole. A positively charged particle is called as a hole. Holes can be produced by thermal energy or by doping. We already discussed. Holes can be produced by thermal energy or by doping. Pure semiconductors are divided into 2 types depending on type of impurities added. Pure semiconductors are divided into 2 types depending on type of impurities. Generally, you can say that there is a impure. Pure is the intrinsic semiconductor. Impure semiconductors are the 2 types. The first one is the N-type semiconductor. Second one is the P-type semiconductor. N-type semiconductor and P-type semiconductor. N-type semiconductor. When we add a pentavalent impurity to pure semiconductor, we get N-type semiconductor. Pentavalent impurity or donor impurity, if you add to the pure semiconductor, what happens means the pentavalent having the 5 electrons, semiconductor having the 4 electrons, To form the covalent bonds, semiconductor requires only 4 electrons. The 4 electrons are formed with the 4 electrons of the arsenic, and one extra electron is there. That electron is donated for the conduction, that is moved into the conduction band. Now you can see what happened. Arsenic and pure silicon is combined. That is called as a N-type material, N-type silicon, or N-type semiconductor. You can also say that N-type semiconductor. You can see, as I mentioned, arsenic has 5 valency electrons. It makes covalent bonds with adjacent 4 electrons of silicon atom. A fifth electron becomes free and enters into the conduction band. Pentavalent impurities donates 1 electron and becomes positive donor ion. Donates 1 electron and becomes positive donor ion. N-type semiconductor, you can see some of the covalent bonds break due to temperature, and electron hole pairs generates electrons are majority and holes are minority. N-type semiconductor, not only by using the impurities, because of the temperature, some of the covalent bonds are broken, and after breaking due to this, electron hole pairs are generated. So because of free electron, donated electron and generated electrons, N-type semiconductor having the more number of electrons and less number of holes. So in the N-type material, majority charge carriers are the electrons, minority charge carriers are the holes. Now we try to discuss about the energy band diagram of N-type semiconductor. You can see valency band and conduction band. In the conduction band, we may having the more number of free electrons, so the Fermi level lies near the conduction band. So what we discussed about the doping hole extrinsic semiconductor. In the extrinsic, we discussed about the N-type semiconductor. So now we try to discuss about the P-type semiconductor, energy band diagram of the P-type semiconductor. So I already explained that P-type semiconductor, when we add trivalent impurities to pure semiconductor, we get the P-type semiconductor. The meaning is, if you add the trivalent impurities or trivalent atoms to the pure semiconductor, then we get the P-type semiconductor. You can see the P-type material is gallium atom. Gallium atom has 3 valency electrons. So 3 valency electron, it makes covalent bonds adjacent 3 silicon atoms. As shown in the figure. There is a deficiency of one covalent bond and create a hole. There is a one deficiency of one covalent bond and create a hole as shown in the figure. So these trivalent atoms accept electron. These trivalent atoms accept electrons from another silicon atom. That's why this is called as a acceptor. They are called as a acceptor atoms. In addition to this, some of the covalent bonds break due to temperature and electron hole pairs are generated. Not only the free holes, but also more number of holes and electrons are generated due to the temperature. Holes are majority charge carriers and electrons are the minority charge carrier. If you take the P-type material having the holes are the majority charge carriers, and N-type material having the electrons are the majority charge carriers, vice versa. So p-type semiconductor energy band diagram you can see. So in the conduction band we may have a less number of electrons, but in the valency band we may having the n number of free holes are there. So that's why the Fermi level is lies nearer to the valency band. The Fermi level is lies nearer to the valency band. So this is about the p-type semiconductor and energy band in p-type semiconductor. So now we try to discuss about the types of semiconductors. We already said the semiconductor can be classified as intrinsic semiconductor and extrinsic semiconductor. Again, extrinsic semiconductors are further classified as n-type semiconductor and p-type semiconductors. First one is the intrinsic semiconductor. The semiconductor in pure form is known as intrinsic semiconductor. I already mentioned. Semiconductor in pure form is known as intrinsic semiconductor. Pure germanium, pure silicon is called as a intrinsic semiconductor. At room temperature, number of electrons equal to the number of holes in the intrinsic semiconductor. The meaning is number of holes are equal to the number of electrons, means there is no free charge carrier to move the current. So at the room temperature, intrinsic semiconductor is act as the insulator. You can see the conduction band and valency band of the intrinsic semiconductor. You can see the Fermi level is in between the conduction band and valency band. So next one is the extrinsic semiconductor. What is the meaning of extrinsic semiconductor? When we add an impurity to pure semiconductor to increase the charge carriers, then it becomes an extrinsic semiconductor. I already mentioned, when we want to increase the charge carriers, we add the impurities. So that semiconductor is called as a extrinsic semiconductor. In extrinsic semiconductor, without breaking the covalent bonds, we can increase the charge carriers. Without breaking the covalent bonds, we can increase the charge carriers. Now we try to discuss about the comparison of semiconductor, that is the intrinsic semiconductor and extrinsic semiconductor. Once again we try to compare. Intrinsic semiconductor. Intrinsic semiconductor, it is in pure form. It is in pure form. Extrinsic semiconductor, already you know that it is found by adding trivalent or pentavalent impurities to a pure semiconductor. Extrinsic means if you add the trivalent or pentavalent impurities to the pure semiconductor, then that semiconductor is called as a extrinsic semiconductor. In the intrinsic semiconductor, holes and electrons are equal. Holes and electrons are equal in the intrinsic semiconductor. Coming to extrinsic semiconductor, number of holes are more in p-type material, number of electrons are more in n-type semiconductor material. P-type material having the more number of holes and n-type material having the more number of electrons. The next one is Fermi levels are lies between valency band and conduction band. The Fermi energy level is in the middle of valency band and the conduction band. Coming to here, where Fermi level lies nearer valency band in p-type, nearer conduction band in n-type. The Fermi level may be aligned with the conduction band or valency band. In the p-type, the Fermi level lies nearer to the valency band. In the N-type, the Fermi level is nearer to the conduction band. The ratio of majority and minority carriers are equal in the intrinsic semiconductor. The ratio of majority and minority carriers are same. Coming to in the extrinsic semiconductor, ratio of majority and minority carriers are equal. Ratio of minority carriers are not equal. So this is about the comparison between the intrinsic semiconductor and extrinsic semiconductor. Now we try to discuss about the comparison between p-type material and n-type material, or p-type semiconductor and n-type semiconductor. Comparison between n-type and p-type semiconductors. N-type semiconductor, p-type semiconductor. We already know that n-type semiconductors are pentavalent impurities are added to the pure form of semiconductor. Then p-type n-type material is formed. If you add the trivalent impurities to the pure form of semiconductor, we will get the p-type material, p-type semiconductor material. N-type material, majority charge carriers are the electrons. The n-type we having the majority charge carriers are electrons, minority charge carriers are holes. Coming to the p-type semiconductors, majority carriers are holes, minority carriers are electrons. Fermi level is near the conduction band in the n-type material. Fermi level is near the valency band in the p-type material. So what we discussed until now is comparison between the intrinsic semiconductor and extrinsic semiconductor. Again we compare between the n-type material and p-type material. Now we try to discuss about majority and minority carriers in p-type semiconductor, majority and minority charge carriers in n-type semiconductor, drift process and the diffusion process. So this is the next topic. What we are going to discuss is majority and minority carriers or p-type and n-type, drift current and diffusion current we are going to discuss. Already we know that the semiconductors divided into n-type and the p-type. So we also discuss extrinsic n-type, how n-type is formed. Again next we discussed about the arsenic atom has 5 valency electrons. Fifth electron is surplus becomes free electron and enter into conduction band. Therefore pentavalent impurity donate 1 electron and becomes positive donor ion. Pentavalent impurity is known as donor. P-type semiconductor, we know that when we add a trivalent impurity we get the pure form of p-type material. So p-type having the 3 valency electron, it makes covalent. There is a deficiency of 1 covalent band and creates a holes. Therefore trivalent impurity accept 1 electron and becomes negative acceptor ion. 1 electron and negative acceptor ion. Trivalent impurity known as acceptor. In the donor atom, in that what is a pentavalent pentavalent impurity donates 1 electron and becomes the positive donor atom. Positive donor atoms are in the n-type material. Negative acceptor ions are in the p-type material. Negative acceptor, positive donor. carriers in p-type material, you know already. In addition to this, some of the covalent bonds break due to temperature and electron hole pairs are generated. Holes are majority charge carriers and electrons are minority charge carriers. You can see p and n type semiconductor. By seeing the diagram you can see how it is. P type material, n type material. Here minority are the electrons in the p type, majority are the holes. So the ions, p-type material ions, you try to remember, in the p-type material one electron is deficient, the electron is accepted and the atom becomes the acceptor ion. When electron is accepted, the charge is minus. That's why the ions, the immovable ions in the p-type material is minus. The immovable ions in the p-type is the minus. Coming to the n-type material, so here in the ion, in the atom will donate the one electron, donating a electron, so that becomes the donor atom, positive donor ion. Positive donor ion, these are the immovable ions. The meaning is immovable positive ion is there and movable electron is there in the donor, in the n-type material. In the p-type material, negative immovable ions are there, positive movable charge carriers are there. Okay, this is the comparison of p and n type with diagrammatically what are there in the p type and n type. Let's see. Acceptor ion, donor ion, minority carriers, majority carriers. So already you know this comparison we can see. Already we seen this comparison. Once again given. So now we try to discuss about the conduction in the semiconductor. So what is the meaning of conduction? How the conduction process takes place in the semiconductor. So here we having the two types of methods are there. The conduction is carried out by means of drift process and diffusion process. A drift process and diffusion process. Drift means applying the external energy to change the direction of the electron. That is called as a drift process. Diffusion means from the high concentration to moving to the low concentration side. So that is called as a diffusion process. Now we try to discuss in detail. Drift process means you can see. So what we are doing is we are applying the external voltage so that the direction of the electrons are moved through the path. Electrons move from external circuit and in conduction band of a semiconductor. Conduction band and valency band is there. Electrons move from external circuit, moving from external circuit and in conduction band, and in conduction band of a semiconductor is known as drift process. Holes move in valency band of a semiconductor. Holes are moved in the valency band of semiconductor. Next one is the diffusion process. So you can see the diffusion process means moving of electrons from higher concentration gradient to lower concentration gradient is known as diffusion process. In the drift we are applying the external energy or external voltage, but in the diffusion there is no external, internally it having the movement. So external with the drift current we may having the some amount of current is flowing there, but in the diffusion process we may don't having the current. Moving of electrons from higher concentration gradient to lower concentration gradient is known as diffusion process. So what we discussed is we discussed about the intrinsic and extrinsic semiconductor, majority and minority carriers, diffusion process and drift process we discussed. So now we try to discuss about the some other topics are there, that is the formation of PN junction, barrier potential, depletion layer, so on. So now we try to discuss about the P and N type semiconductor, formation of P type PN junction diode. You can see the diagram. So we having the diagram with the P type material and N type material. So how P and N type material is formed, you can see diagrammatically, very simple. You can see there formation of PN junction diode. Now you can see that diagram. So what we are taking is we are making the P type material, N type material together. P type material, N type material. In the P type material we having the holes and immovable acceptor ions. In the N type we having the electrons and immovable donor atoms are there. So whenever we are combined both the P type material and N type material, due to the diffusion process, you can see the electrons and holes at the junctions are recombined, and the electrons holes are eliminated or depleted at the junction. So the junction where the electrons where the moving charge carriers are depleted, that region is called as a depletion region. In the depletion region we don't have any charge carriers, so that is any charge carriers are there. So this side is here we having only the minus acceptor ions in the P type. N type we may having the positive donor atoms. So from the N type, if any electrons are try to move into the P type, the immovable acceptor ions are try to oppose the movement of the holes into the P type, and electrons from the P side may try to enter into the N type. The donor atom positive charge try to oppose the entering of the holes, so that the junction barrier is developed there. So that junction is called as a depletion region. That barrier is called as a potential barrier, VB. So there at the junction some potential barrier is existed. We need to overcome that potential barrier, then only the electrons from the N type to move to the P type. Without breaking that potential barrier, does not move into the N to P. So now we can see, once again we try to discuss what happened. A PN junction is formed if donor impurities are introduced into one side and acceptor impurities into other side of a single crystal of semiconductor. So what we are doing is, in the PN junction, how it is forming means, first we take the intrinsic semiconductor, pure form semiconductor, and we introduce the donor impurities into one side and acceptor impurities into other side of a single crystal of semiconductor. Initially there are P-type carriers to the left side of the junction and N-type carriers to the right side of junction, shown in the figure. On formation of PN junction, electrons from N layer and holes from P layer diffuse towards the junction. On formation of PN junction, electrons from N layer and holes from P layer diffuses towards the junction, and recombination takes place at the junction and leaves an immovable positive donor ions at N side and negative acceptor ions at P side. What happens? Diffuse towards the junction and recombination takes place at the junction and leaves an immovable positive donor ions at N side and negative acceptor ions at P side. A positive potential barrier develops at the junction whose voltage is zero point 0.3 volts for germanium and 0.7 volt for silicon. So then for the diffusion stops and results a depletion region at the junction. A potential barrier is developed at the junction whose voltage is zero point 0.3 volts for germanium and 0.7 volts for silicon. If we overcome this potential barrier voltage, then only electrons move from the N to P side. So then for the diffusion stops and result a depletion region at the junction. So what is the depletion region? Depletion region, since the region of the junction is depleted of mobile charges, it is called the depletion region. That is, since the region of the junction is depleted of mobile charges, it is called the depletion region or the space charge region or the transition region. The thickness of this region is of the order of 0.5 micrometer. The thickness of this region is 0.5 micrometer. You can see the circuit symbol of a PN junction diode. The arrowhead indicates the direction of conventional current flow, anode and cathode. Anode and cathode, we can see anode and cathode. So now what we discussed is the formation of PN junction, barrier potential, depletion region we discussed in this class. So in the next class we try to discuss remaining topics. Okay, so today we stop at the part 2 PN junction 2 here. Thank you.